This chapter, you guys have to understand about these three mechanisms. Okay, what is the majority? What is the main point? Okay, so in some of the materials, like alloying, we have talked about the alloying material like germanium, right? Germanium and tin, and something like silicon, right? So there is an alloying process. Because silicon can be accommodated with maybe silicon Si-24. Lithium Si-24. Later, sorry. Si-4, lithium, and Si-24. 24 lithium, and then just only 4 silicon can accommodate. So this is like high efficiency. So, and also TR2. TR2 is also one of the insertion. The most abundant materials like carbon. Okay, carbon is very cheaper materials and put it as a layer by layer structure. So these things can be insertion and extraction, okay, very different. And also, but it is the low capacity, okay, low capacity. Cylindrical capacity is about 380, something like that. Later we have a table to show some comparison. Okay. The cylindrical capacity is just based on the cylindrical calculation, okay, cylindrical calculation. So. In general, the cylindrical calculation and efficiency we could see using some cooling efficiency to see about whether if the for example cylindrical capacity is 400 and then cooling efficiency is 100, and that means these materials can reach 100% of cooling efficiency, which is 400 cylindrical capacity, almost equal. Okay, so but actually there's not quite hard, difficult to maintain always that charge and discharge that cooling efficiency and always maintain that high efficiency. This is quite tough. So we have some example to show you guys. Okay. So last time we talked about the lithium, and then the lithium is quite similar to the silicon, but compared to the silicon, the tin can accommodate about 4.4 lithium. Okay, 4.4 lithium. So that means compared to the carbon is Li6. Okay. So 6 carbon just only accommodate 1 lithium. So therefore, the cylindrical capacity is low. But for the tin, cylindrical capacity is much higher, which is about 500 to 600. So, but unfortunately, given the charge and discharge, tin is quite soft. Okay, it's quite soft. So therefore, charging, that means the lithium is insertion, right? Insertion and insertion again. Extraction again, so which will making the mechanical property will be degraded or will be downgraded, and therefore it will be break. Okay, break. When the tin is break, so that means you will see that the battery will be expanded. Okay, will be expanded. Okay. So the scientists developed some of the materials like alloying materials. Like nickel alloying, okay, nickel alloying. So this is able to making the charge and discharge can be sustained to more stable, okay, to more stable. So not only the nickel, but also some of the other metal transition, okay, metal transition still can be consideration, like the copper, steel, okay, steel is also soft. So those of the materials that it is easy to observe about the binary phase diagram. The binary phase diagram, right? So you should be able to find out the suitable or best composition, okay, composition of the nickel, for example, and the tin. You can see about the phase diagram to see about what phase composition is the best, okay. But what composition is the best still need to do some experiment, okay. You have to modulate about the percentage of the tin or percentage of the nickel, okay, and then to see about the best condition. The best condition still need to observe about the charge and discharge, okay, cooling efficiency, and also about the mechanical property, including about the volume expansion, okay, volume expansion. So this is a quite long-term story, long-term experiment to do, okay. So this is another idea that we just talked about the copper, okay. For example, for the traditional silicon, okay, traditional silicon, without copper, later we have another slide, okay. The silicon has a stronger volume expansion, but here you can see lithium and silicon alloy, okay, alloy material can be utilized as a negative electron, okay, negative electron, which is a half cell. So during the charge and discharge, charge means the distillation and the distillation. So you can see here, if we mix lithium and silicon alloy into the copper, and the copper alloy or copper particle or copper flake, okay, flake. And actually you can see during charge and discharge, actually the lithium will progressively, silicon will progressively expand their volume, okay, their volume. So therefore, here, because of the copper flake, okay, there's can accommodate more space, okay, more pores. So therefore, you can see even during charge and discharge, the silicon has been expand their volume, but still you can see because the inside of the silicon, the majority is the porous, okay, porous structure. So you can see here, the porous structure can accommodate more space, okay, just see more volume. So I would say, for example, you have one silicon right here. Okay, here is the silicon. So lithium in and lithium out. And finally, you will see something like that. The lithium, the silicon will be looks like that. It will expand. But if today we have something like the porous, so lithium in, lithium out. Because here is a porous silicon. This is a solid silicon. The solid silicon will be expanded, but the porous, because inside has a lot of pores, so which can accommodate the volume expansion. Okay, accommodate the volume expansion. Okay, like if you look at about this, okay, distillation, because here is another porous structure. So even charge and discharge, the lithium and the silicon alloy will expand it, okay, will expand it. And then this kind of compound will break, okay, okay. So just like you know, like a sponge squeeze, okay, you can squeeze it. You can accommodate more volume expansion. Okay, volume expansion. So for the HEP cell, okay, for the HEP cell, the mostly important idea is how to select one of the materials, like these materials, can accommodate more space, which can suffer the volume expansion. Okay, the volume expansion. So, because the volume expansion determines about lifetime, the least lifetime, right? This battery lifetime. Because during the charging and discharge, although the cylindrical, we can see about this here. Okay, we can switch to page 18. You can see here. This is the battery materials and their performance. Okay, let's compare about here carbon. Okay, carbon has a different carbon material, like a carbonless. Okay, carbonless means there's hard carbon, soft carbon, and intermediate carbon. Later on, I will show you what is the soft carbon, what is the hard carbon. There's something a little bit different. But the carbon materials, you can see the cylindrical capacity is 200 to 600. It is less than 600, no more than 600, no more than 600. But carbon is very cost is quite low, okay, and quite safety, okay. So everything it is able to find out the easy to get the carbon, okay, easy to get the carbon. But now, if you look at about the silicon, cylindrical capacity is 4,000, right? 4,200. So it's at least one order higher than the carbon, right? Quite high. So that's why now you can see about the commercial lithium-ion battery still using the silicon, okay, using the silicon. And of course they have some technology to do, okay. Like they couple lithium outside copper of carbon, okay. So because carbon is the soft, more soft, so can accommodate some of the volume expansion from the silicon, okay. So next is also using the carbon still having some of the CNT and graphene. You know, CNT is the nail wire, right? It's the nail wire. But the carbon is like a flake, layer by layer, layer by layer. So which is dense, very dense, right? So during charge and discharge, I would say, yeah, it is still have limitation space. For example, let's look at here. Okay, let's do it. Later I will explain again about this slide. Let's look at about the graphite. Okay, graphite. This graphite you can see the layer by layer structure, right? Here is the layer by layer structure. So there is a space to making the lithium to accommodate, right, in this position. Okay, right, this position. Okay, but if you look at about, okay, that's good because there's some of the space layer by layer to penetrate the lithium inside. But what about nail wire? Here, what about this nail tube, right? If you look at about, sorry. If you look at the carbon nanotube, okay, carbon nanotube, you can see here the lithium is SLI accommodate 2 carbon, right? So compared to graphite, is LI accommodate 6 carbon, right? So which has a much higher cylindrical capacity, right? Which can reach 1,000, over 1,000. Right? And then you can see the lithium can be accommodated right here, right? Accommodated right here. So there's a lot of the space, okay? A lot of space And the nanotube, okay, nanotube can suffer more volume expansion. Do you know? Because carbon, for the graphite, it looks like that, layer by layer. Graphite materials. But for the CNT, it's will be like CNT. Here is the CNT. Right? Here is the CNT. So CNT, you can see there's a surface inside and outside. Inside and outside. Out and outside area. So there's a high surface to volume ratio. Right? So therefore, compared to the traditional graphite, CNT can accommodate more needs. So that's why the CNT cylindrical capacity reversible is a reversible. It reaches over the 1,000. Okay, later we will go back to here. Okay, so the main point is how to get a high cylindrical capacity and less volume expansion. Okay, so you have a lot of material can choose. Okay. Cooling efficiency, okay, now we introduce about cooling efficiency. Cooling efficiency is quite important, also called the Faraday efficiency, okay, or the current efficiency. And this is described that the charge efficiency by which electrons are transferred in the battery. So that means if one electron transfer out, that means one lithium will be accommodate to the anode side, right? Because one electron out, one lithium positive should be in. Okay, we have the first slide to show that, right? So you can base on this to describe the charge efficiency by which electrons are transferred in the battery. So cooling efficiency we call CE, okay, is the ratio of the total charge extract from the battery, okay, to total charge put in the battery over a whole full cycle, okay, over the full cycle. So that means if you look about this, okay, this is a discharge, right? And then this is a charge, right? Charge will be right here. So the electron will be, the charge will flow to here, and electron will flow to this side, right? Flow to this side. So let's look at about the discharge. You can see the electron flow to this way, right? So therefore the lithium will be accommodated, right? Accommodated to here. So that means we can total to calculate about how much lithium accommodate to here, and then how much electron transfer through the external load. Okay. So overall, the efficiency we can calculate. Okay. But some of the, because you know there's a SEI formation, right? SEI formation, that's a cover layer, a surface cover layer. So this cover layer is a SEI, and this SEI here we have explained, right? This SEI become a barrier that making the lithium cannot transfer out, right? Cannot transfer out. So therefore, the cooling efficiency will go down, will be reduced. So that's why usually for the lithium-ion battery, the first cycle is the best. First cycle is the best because there is no SDI, right? But the second cycle, third cycle, three cycle, SDI getting thicker and thicker. Some of the lithium is been I would say been hindered, right? Been hindered. That means that the lithium need to overcome, right? So therefore, one of the once the lithium been cannot reverse, and then the cooling efficiency will drop. Okay. Okay. So this slide, later I will explain about this the chart, the cooling efficiency, okay, and energy density, okay. And this slide is a table that tells us about energy density, okay, the energy density as a function of the year, okay. For example, Tesla current, this is the type, okay. One of the type is called 2170. This is the cell, and there's also this cell is in form of the Panasonic 6752. This is just for your reference, anyway. And usually, I would say this is the energy density. We wanted to make the energy density as high as possible. Okay, so you can see the energy density can be calculated by the volume or by the weight, right? Here is the upper side is by the volume. Volume doesn't mean the watt-hour per liter. Per liter doesn't mean the per square cubic, okay? And or per weight. So it depends on the unit. It depends on that. Anyway, it is the same calculation. Okay, the same calculation for the energy density. Okay, but anyway, we wanted to make the energy density as high as possible. So several companies now they are engaged to develop the high energy density of the battery. Okay, so most of the abundant company like Tesla and Panasonic, they are doing some manufacturing. Like the Tesla Model 3 have the energy density about 260. Now it is already reached over than 350 or even more high. Okay, more high. Because this energy density, if we get a higher energy density, that means the electrical car can transfer, can charge one time and then maintain for a longer distance. Okay, maintain a longer distance. Okay, now let's calculate about energy density. So what is the energy density? Okay, so if you look about this equation, okay, you can see we have to say about the energy density can be unit, can be volume, or can be weight, right? Can be weight. So now this equation is calculated by the volume, okay, volumetric, okay, volumetric. So we call it EV here, okay, EV. So EV is a volumetric energy density. That means that the unit is watt per hour, okay, for 1 hour and per liter, okay. That means this battery can suffer. For example, you have 1 watt 1 hour. That means you can deliver 1 watt and then suffer for 1 hour. Do you understand? For example, this is the battery. Okay, this is the battery. Okay, if this battery energy density is 1 watt per liter, 1 watt hour per liter. Per liter doesn't mean the size. Okay, the size. So that means this battery can provide 1 watt and for 1 hour. Okay, after 1 hour, there is no electricity. Okay, you have to recharge again. Okay, and for example, you have the 100. That means you can provide 100 watt per hour. Okay, so you can depend on your cell phone or your portable device. You can see about your portable device. Back side has power consumption, right? You have the power consumption. For example, your laptop is 90 watt, okay, 90 watts. So that means, okay, you can use this battery to charge your laptop, okay. So this is the energy density calculation. So this is the unit EV, okay. So EV is the the capital V is the average cell voltage. Is here, average cell voltage. That means how much voltage, okay, how much voltage this battery have, okay. So you have the battery, right? You have battery output voltage, right? And then MA, okay, MA is the materials active material, the mass of the active materials. Okay, that means by weight, right? Calculate by weight. The active materials, that means all the materials, whatever for the negative or positive side, anode or cathode, all the material we call the active materials. Okay, like the carbon is also active materials. Silicon is also an active material. Active materials, that means which can accommodate for the lithium. Okay, so we call it active materials. So this active materials mass, okay, multiplied by specific capacity. Okay, right? Specific capacity, you know, is about similar to the cylindrical capacity. Okay, cylindrical capacity, because you know about, for example, carbon has a cylindrical capacity is 300, right? So you can apply. Oh, here CS is 300, then 8 hours per gram. Okay, so this is a specific capacity. So specific capacity, the unit, okay, is the milliamp hour per gram. Okay, per gram. Specific capacity. This capacity, that means can provide how many current output. Okay, how many current output. Okay, so usually you have the table. For example, you have the table right here. You have the table like a silicon, right? You have the 4,212 capacity. This is a milliamp per hour per gram, right? That means 1 gram, just only 1 gram, can provide almost 2 amp. This is a milliamp, right? And 400, that means silicon has a 4 amp, right? Over than 4 amp per hour per gram. Is that okay? Per gram. Over than 4 hours. Because this is milliamp, right? Milliamp, and then there's a 4,000, right? So 4.2. That means 4.2 amp. This is quite high. That means the current is quite high. Okay, the current is quite high, and the current is quite high is good for some high power, right? Because some of the devices need high power, right? High power, high current. So this can be used for high power. You can see because higher specific capacity, okay, high energy density, okay, high energy density, and it is also good safety. Okay. So now, oh, sorry. So now, because here we have the output voltage and active mass and cylindrical capacity, and you have to divide it about the total mass. Okay, total mass. That the first term. Let's calculate about the first term. The first term you can see is the Mi. Okay, Mi here is the mass of the sulfur, carbon, or the binder. Okay. For example, here we take an example is the carbon mixed with the sulfur. Okay, and of course inside you have some binder, right? You cannot only use the carbon, right? if you just only use the carbon, because it's the powder, you cannot make a paste. So you have to apply some binder and mix a solution paste. So therefore you can screen printing, right? Or data braid. So you can print it on the electrode. Do you understand? It's okay, right? Just like here, right? You have the powder, right? You have to provide the powder, carbon, and polymer, right? Polymer is a binder to making everything together, right? Become a solution paste. So therefore we can print it on the electrode, right? Row to row, right? So you have to calculate all the weight, okay? All the weight, carbon how much, binder how much weight, and to calculate, okay? So you have to calculate here, okay? So mass, okay? So the mass, because not only the carbon, maybe you have another additive, like whatever, titanium, right? Like copper, because we have some of the mixture materials, right? So therefore, that's why we have the summation overall, right? Is that okay? Right? You have the summation. So you have the maybe of the M1 is the carbon, M2 is the Tr2, M3 is some of the other materials, okay, silicon. If you have some new development materials, so you have to summary overall, and then you have to divide it by density here, and rho I is the density of the sulfur and carbon and binder. Because the mass divided by density is volume, right? Mass divided by density is the volume. Because here should be volume, right? Right? Here should be volume, and upper should be output pump, right? Is that okay? Okay, so. And then also, because the unit, okay, so you have to divide it by epsilon, okay? Epsilon is the diameter, porosity of the cathode, okay, of the cathode. And then second term, okay, second term. It depends on, for example, of course you have the lithium, right? Because the main materials is the lithium. So you still have to use in the lithium, because the lithium, the weight of the lithium, right? And then the lithium divided by lithium density, okay? And then the third term, okay, third term is that you have to calculate about the DI. DI, what is the DI here? DI is the thickness of the alloy. Because DI here, there's an electrode, right? You have the electrode, like an alloy electrode and copper electrode, right? So you still need to divide it by this DI, right? And this electrode, DI is the thickness. You have to count the thickness, okay? And also copper corrector, right? And therefore you have to summation, because you have the two different electrodes. One is the copper, one is the electrode, right? So you have to sum, right? You have to sum together. And then, because this is only the thickness, right? But you still need to multiply by S. S is the surface area. So the surface area multiplied by thickness is the volume, right? Is that okay? Surface area multiplied by thickness is the volume, right? Okay, so this is the summation of the volume for electron. Okay, so this is the energy density calculation. Usually we can take this kind of calculation. So you should be able to. Here is the paper. Maybe you can take this paper to read. Okay. So anyway, you have a layer, one layer, two layers, three layers, right? So you have to overall to sum, okay, together. Overall to sum together. So that means if you have the less materials, okay, you have the less materials, you have a higher output voltage, and then also the mass, higher mass of the active materials, and you should be able to get the higher energy density. Okay, and of course this term is very important. If the cylindrical capacity CS is too low, of course here this term will be dominant the output energy density. Okay, so CS, that's why it's quite important, right? Because the mass always fixed, right? Voltage depends on the materials used the lead, right? If you use the lead, one of the materials, the voltage is already determined, right? And CS is depends on the capacity. Okay. So most commercial anode is graphite. Okay, now we introduce to the graphite. Graphite has last time we have talked about one lithium, right? Graphite allow the interconnection. Okay, interconnection. Like the one lithium with 6 carbon atoms. So usually we have like LiC6. So there's a lot of the schematic diagram to take this example to show about it is quite reversible. Okay, and currently it also have a lot of the commercial device, commercial battery using the graphite. Okay, graphite. So and the diffusion rate is also quite important factor to monitoring about the performance. Okay, so the diffusion rate of the lithium, into the graphite, carbon materials is between 10 times minus, it's quite low, 10 times minus 12, and to minus 6, okay, minus 6. So how to make the diffusion rate become fast is become very important. So people, okay, scientists, because graphite, we know that some of the graphite has high conductivity. So people, they can develop some of the new materials or some doping, okay, to make the lithium transfer fast. So-called the CNT or the graphene, okay, layer by layer, graphene. So it can increase the diffusion rate, okay, increase the diffusion rate. But anyway, this is quite low cost. Cost is quite low, okay. So this slide we is talk about the dendrite formation. Dendrite formation is quite frequently to observe, okay, in the lithium-ion battery for the commercialized, okay. What is the dendrite formation? For example, now we provide the lithium anode as an anode. We just provide lithium as an anode side, okay. And then here is the cathode side, okay, it's the cathode side. So of course we have a separator right here, okay, we have a separator right here. So during the transfer, charge and discharge, okay, because the lithium will diffuse in and out, diffuse in and out, okay. So as you can see, there's an SEI being formed, okay, SEI being formed. But unfortunately, there's a very important that during charge and discharge, the lithium will progressively grow, okay, grow on the lithium anode side, okay, lithium anode side. So therefore, it will become, this is a cross-section image, that because the metal provide a substrate, right? Provide a substrate. So as you can see, the lithium will be accommodated to here, and then again, over again, and over again, and you can see during the long cycling charge, here the lithium will be grow. So you can see the lithium grow just like a little wire in dendrite, right? And this is because this is the metal, right? So there's a mechanical strength is quite strong. So therefore, it will be penetrate to the separator. Okay. Once it penetrates to the separator, because this is the cathode and anode side, right? So it's just like a bump, right? Like a bump, right? Bump, boom, right? So it is quite dangerous, right? So that's why during if you take an airplane, right? The assistant will ask you, did you have the battery in your luggage, right? In your luggage. For the hand carry is okay. Hand carry will be okay because you hand carry to your seat. So once the there's something happen explode that we can observe. But if the luggage is just sent for the transfer, because nobody there, but during shaking, once it penetrates, it should be explode, right? It should explode, and nobody cares, right? So therefore, it is quite dangerous. So during you have some travel, if you are traveling, yeah, the airplane assistant will always ask you, did you have some battery in your luggage, okay? Non-hand carrier luggage. So anyway, this is the issue, okay? So active materials, usually this is just some comparison, okay? For you understand about some of the popular materials, okay? Graphite is right here. You can see here is the capacity, okay? Capacity, amp hour per kilo, okay? And this is the potential. Potential doesn't mean the output voltage, okay? Because the output voltage, as I say, the output voltage depends on the materials. Titanium oxide, dioxide, has output voltage 1.2. Okay, some metal oxide, output voltage is right here. Okay, it's right here. But mostly that we want to observe is the capacity. Okay, here is the capacity. Okay, this thing is right here. It has a high capacity, right? Because this thing is a source, can provide a lot of the lithium, no problem. But unfortunately, there's a low output voltage for the lithium metal. Okay, and also lithium metal is just like a substrate, so easy to make a dendrite formation. Okay, like you grow like a CVD, right? CVD vapor transfer and condense to the metal substrate, and again, so you can grow the materials like a CVD. You know, dendrite formation looks like a CVD. Just like a CVD, dendrite formation is deep because of the charge. We apply the electricity, so therefore they can charge, discharge, charge and discharge. But CVD, we provide the vapor to the system, right? Is that okay? We provide the CVD to the CVD looks like a CVD. You know, you have the source right here, right? The powder right here, and then you increase the temperature, and then the vapor will accommodate to the substrate, right? And then grow the materials, right? But for the dendrite formation, we apply the electricity. We apply bias, right? So you have the charge and discharge, charge and discharge. So of course you can grow. Okay. So that's why you can see here the green side. Okay, there is alloy materials. Okay, around this spot. Okay, you have a lot of choice: silicon, germanium, aluminum, tin, and antimony. Okay, so you have a lot of choice for these. So mostly abundant materials and commercial materials you can find here. Okay, like germanium, silicon, and also tin. Germanium is more expensive. Okay, more expensive. And some of the metal oxide. Okay, metal oxide, metal transition oxide, like conversion, right? Conversion. M is the metal, and O is the oxide. Okay, metal oxide is right in this position. Okay, right in this position. So those are conversion. Okay, using the conversion mechanism. Right, right here. Conversion. Okay, conversion.
Professor, sport one.
Oh, it's time up. Okay, let's take a break.